So today we're going to talk about comparing two means. We're going to talk about t-tests and the assumptions of t-tests, and we're going to do this in a few different ways. So first, to review, variables can be either continuous or categorical. And the little symbols you see on the screen are what JUMP shows you. So a blue ramp for continuous variables and two different kind of histograms or bar graphs for categorical variables. So we could be interested in these variables in terms of their means or medians or mode, and we might be interested in their variation in terms of standard deviation and standard error, like you learned about previously. But next we're going to talk about research questions, hypotheses, and predictions, because we're going to start making some statistical tests. So first of all, the scientific method starts with an observation. And then from that observation, you frame a research question. And that research question allows you to formulate testable hypotheses. So hypotheses are educated guesses about why you're seeing the observation that you're seeing. And then once you've designed a study, you might have a prediction for the outcome of a particular study based on your hypothesis. So then you're going to develop and test predictions, and we're going to gather data from which you can test these predictions, and then you're going to analyze the data, and you'll either decide to reject the hypothesis or you're going to accept your hypothesis, and then you're going to refine your hypothesis. And sometimes that means you might develop a new experiment with new testable predictions, or sometimes your results will lead you to develop more general theories, and then you move on to making new observations about some new question. So real quickly, a hypothesis, like I said, is an educated guess about what and why something is happening. A prediction is an educated guess as well, but it's more specific to the results of an experiment that you're designing to test the hypothesis that you're interested in. And so an example might be, you might think that eutrophication, which is excess nutrients in the environment, will lead to increased algal growth. That's your hypothesis. But you need to design a study where you'd actually add nitrogen to a stream, and then your prediction would be, if I add nitrogen to the stream, then algal growth will increase. That would be your specific prediction. So just to be very clear, we cannot ever prove that our hypothesis is correct. This is a limitation of the scientific method. And this is one of the most aggravating points, I think, about scientists interfacing with politicians and policy, that they want us to have proof. They want us to have this unequivocal evidence. We just can't do that. So what science can do, though, is we can disprove what's called the null hypothesis. And a null hypothesis is basically the hypothesis of no effect. So it's kind of like you're innocent until proven guilty. We're going to assume that there's no effect, whatever it is that we're studying, until there's evidence that indicates otherwise. And so this is kind of built on what's called Occam's razor, so that the simplest explanation is often the truth. And Occam's razor kind of cuts away unnecessary complexity. So here's a little joke for you. I need a laugh track. Ha, ha, ha. Right? Occam choosing a razor, he's thinking, oh my God, they're both too complicated. Great. Okay, so back to the null hypothesis and this idea. We shorthand null hypothesis as H sub 0. And for most ecology questions, the null hypothesis is that the pattern we see in nature is just due to chance alone or some random effect. It's not actually due to something true or some real effect. And if there was a real pattern out there, then the probability that it's due to chance alone would be very, very small. Okay? So, and if this probability that it's due to chance alone is less than 5% of the time, or p less than 0.05, then the pattern is probably true. And so this is where this idea of the p-value comes from. And so we're going to come back to this, and we're going to see how this works in real life. Okay, so for example, there's an ant called the Western thatching ant, Formica obscuripes. Okay, so here's a picture of this ant, and it builds these huge ant mounds for hundreds of thousands of workers, and they look like this out in the forest, and you can find these around Washington. So what if we had a question, we made an observation, wow, looks like there's a lot of ant mounds in these forests, or compared to the fields or something. Maybe you have a research question. Are there more ant mounds in fields or forests? So for example, this could be our research question, and we would want to consider two populations of interest. One would be all of the ant mounds in all of the forests of the world. And the other population would be all of the ant mounds in all of the fields of the world. Okay, so if you think about these two big populations, I think of them as like these nebulous, unknowable populations. Okay. And if you could count up all of the ant mounds in all of the fields and all of the forests in the entire world, you would know the answer to this question. Okay. But we can't know that. We can't possibly count up all of those ant mounds. So these population level means the average number of ant mounds in the field versus the average number of ant mounds in the forest in reality is unknowable. Okay. So we use Greek letters to talk about what are called population parameters, and all population parameters are unknowable. And so we use the Greek letter mu to talk about the population means in the forest versus the population means in the field. So the cool thing about population level parameters is that we can estimate them using sample statistics, okay? And we denote statistics with Roman letters. And so we take a random sample in the forest and we compare it to a random sample in the fields, and we calculate sample means. And we call these Y bar. So the Y bar in the forest versus the Y bar in the field. Okay, so now we're sampling from these populations. Now, Y bar is a good estimator of mu when your sample size is greater than 10, roughly, right? So you need a large sample size is basically what this is saying. And so your samples should be large and they should be collected randomly to be doing appropriate statistical work. So today we're going to learn how to statistically compare two means. We're going to ask this question, are there more mounds in fields or forests? And the general form of the null hypothesis for a comparison of two means would be written like this. H naught, the null hypothesis, is basically mu1 is equal to mu2. Okay. Now, a specific form of the null hypothesis for this example would be H naught, H sub 0. Mu of the forest is equal to the mu in the fields. Note, your hypothesis is at the population level, but your test is at the sample level. Okay, so here's this example. We went out to several forest and field sites and we counted the ant nests. And so you can see the data in this table. So first of all, is there a difference in the number of ant nests in the fields and the forests? Well, my sampling effort was slightly different. I have 6 samples from forests and 4 from fields. I look at the numbers and there's a lot of high numbers for the field, right? Who knows? This is why we need statistics. We can't just look at the data and say anything. So the next step we could do is we could calculate the sample means, the Y bars. Okay, now we have a mean of 7 ant nests in the forest compared to 10.75 in the field. Now is there a difference? We still don't know. We could look at the variation around each mean, right? And we could use standard deviation or standard error, okay? So here's some bars showing the mean and the standard deviation. Now is there a difference? Well, we still don't know, because look at those bars. They're kind of close. I don't know. Who knows? This is why we need statistics. We need to run a statistical test to see whether there is an actual difference between the number of ant mounds in forest versus the field. We can't just look at it. So we're going to run what's called a resampling test first. And what we're going to do is we're going to get these sample means, 7 and 10.75. Then we're going to calculate the difference between them. And it looks like there's about a negative 3.75 nest difference in reality. Then we're going to shuffle. We're going to mix up all the data between the forest and the field. And we're going to recalculate the means and recalculate the diff value. And we're going to do this not just a few times. We're going to do this 10,000 times. And this is how a resampling test works. We have our mean, we have our difference. We're going to shuffle the data, recalculate the means, recalculate the difference, and do it 10,000 times to create a distribution of 10,000 possible random differences in terms of the numbers of ant mounds on average between forests and fields. And then we can compare our real value to that distribution of random values and see how likely it might be due to just chance alone. So that's how a resampling test works. So we're going to do this over in Excel. So I need you to shut this video off and watch the next one.